All right, so today, guys, we're going to go over standing waves, which we sort of introduced yesterday a little bit when we saw the Tacoma Narrows Bridge video, okay, and we talked about how these waves, this wave energy kept getting imparted to the bridge, and it just kept traveling along the bridge, reflecting off the ends, okay, and because those waves never left and more kept getting put on, the amplitude of the movement of the bridge just kept increasing until the bridge collapsed. Okay, so we're going to look at what standing waves are, how they happen. Okay, I'll make some standing waves with the spring up here. Okay, and you'll be able to kind of see the effects of all of this. Okay, and how interference, constructive and destructive, play a big part in the shape of the standing wave and stuff like that. All right, so we got to look at how standing waves result from repeating patterns of interference, both constructive and destructive. Okay, examine how those patterns are formed. Okay, and we kind of talked about that. It's a matter of there's wave energy. If all the wave energy is the same wavelength, it's traveling in the same medium, it has the same speed, it's all the same frequency, then you're going to get these patterns of interference that are going to get set up. Okay, and then we're going to look at the proper names for areas of destructive and constructive interference. And then we're going to look at some of the problem solving to do with standing waves, air columns in particular, okay, and things like that. So that's what we'll be looking at today. All right, so a standing wave is an effect that can occur when two or more waves travel through the same place at the same time. Okay, the pattern itself is a result of constructive and destructive interference from both the waves that are being generated and the waves that are simply reflecting back and forth that have already been generated. Okay, so the figure below illustrates the structure of several standing waves. So I'm going to actually show you these here in just a minute with the spring. Okay, but the simplest standing wave pattern that can form is this first one on the bottom. All right, now, how many wavelengths are on that picture on the bottom one? Less than one. Well, not zero, because there's a wave there. Half. Yeah, there's half, right? A full wave cycle looks like this, right? There's an up and a down. We're only seeing that much right now. So there's half a wavelength on the spring or string or whatever it is that's being oscillated there. Okay. In the second one, there is a full wavelength. Okay. This is a full wavelength here, and this would be how many wavelengths here? 1.5. Okay. Now, if I want to make this pattern on the spring, okay, I would have to shake the spring or the string, whatever, at a certain frequency. Okay, we call that the first frequency that forms the most basic standing wave pattern. It's called the fundamental frequency because it's the first one that makes it. Okay, if I want to make this frequency, if I want to make this standing wave pattern, how much faster do I have to oscillate than compared to the first? Okay, I'm gonna cut the wavelength in half. Okay, and yesterday we had a question, okay, that we were working on that said, if I want to make waves longer, I need to shake the spring at higher or lower. Okay, I'm making waves with a shorter wavelength, so I want to shake it faster. Okay, how many times faster do I need to shake it if I'm going to half the wavelength? Twice as much. So this would be F2. Okay, this would be F3. If I want to get these wave patterns, they are always a multiple of the fundamental. Okay, so if the fundamental frequency occurred when I was shaking this at 5 hertz, I would have to shake it at 10 hertz to get this one and 15 hertz to get that one. All right, everybody okay with that? All right, so I'll show you here what this looks like on a real spring. Okay, so those standing waves look a lot like the ones we saw on the Tacoma Narrows video yesterday. Okay, they were just on a bridge instead of a spring. A spring is better for them. Okay, bridge is bad, right? But they're standing waves nonetheless. They work in exactly the same way. All right, so if we're looking at the picture, if we could, like, if we freeze framed one of the oscillations there that we were looking at, okay, the fundamental frequency is the top picture here, all right? And so the length of the spring in this one is half the wavelength of the waves, all right? Is that okay with everybody? And so if I know how long the spring is, I know the wavelength is twice that. Yeah, okay? And then for the second one, okay, I've got 2 of these areas of constructive interference, so I know that the length of the spring is equal to 1 wavelength. And then in the bottom one there, I've got 1.5 wavelengths on the spring, so the length of the spring equals 1.5 times lambda. Now, the areas of constructive interference, that's here and here, are called antinodes. Okay? The areas of destructive interference, here, 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 and here, are called nodes. Okay? A node is an area of complete destructive interference. An antinode is an area of complete constructive interference. Okay? Those are terms you're going to need to know. Everybody with me there? Okay. The number of antinodes that you see is equal to the frequency number. You get on the fundamental frequency, or F1, there's one antinode. Okay. For the harmonics after that, okay, it's F2, it's F3, okay, and so on and so on. Right, so this is what we would call the fundamental or the first harmonic frequency. Okay, this is the second harmonic frequency, the third harmonic frequency. We call them harmonic because they resonate. Okay, if they're harmonious, they're resonating. Okay, and we're getting that wave pattern. If I don't shake that at a constant frequency, I just get a jumbled mess on the spring. Okay, I have to make sure I maintain that frequency throughout the entire time. Okay, so like we said, the antinodes are the places where maximum vibration occurs because there is constructive interference going on at that point. Okay, so what we're using here, guys, we don't use this term here. We don't use the terms overtones. Okay, we use, this is the first harmonic. Okay, the second harmonic. Okay, third harmonic, and so on. Okay, making sense? All right. Okay, so each standing wave pattern is produced at a unique frequency. Okay, and that frequency changes if I change the properties of the medium. Okay, it just so happened that Tyler and I didn't change how far apart we were. Had I taken a step back, I'd have put more tension in the spring, and I would have had to use a different frequency to cause those patterns to form because I would have changed the speed at which the waves would travel on the string. This is how you tune a string instrument. Okay, so if you pluck your guitar and the sound isn't right, you crank on the little tensioners on the top, okay, they put more tension in the string, which causes the waves to travel at a different speed on the string, which causes them to have a different wavelength, which causes them to have a different frequency, okay? So once you've done that, then your guitar makes a slightly different sound, okay, and that's what we're doing with that, okay? By changing the tension in the spring, we can change the frequency at which it vibrates, and that changes the tone or the pitch, okay, of the sound. Does that sort of make sense? All right, so like we said here, okay, these are our different frequencies here. Like we said, we don't use the terms overtone, we just use harmonics. Okay, so the fundamental is the first harmonic, okay, and so on and so on. Remembering here that this is half a wavelength, this is one full wavelength, 1.5 wavelengths, this is 2 wavelengths. We got to be able to identify stuff like that from a diagram. Okay, and remember that these are multiples of each other. So if F1 is 10 hertz, then F2 is 20 hertz, F3 is 30 hertz. It's always going to be a multiple of the first one. Okay, and this is how you would create like different musical octaves, okay, on a string instrument. If I want to create a really low frequency sound, I use almost the entire length of the string. Okay, but if I want to produce a higher frequency sound, what I do is I pinch the string at a distance that would now be another harmonic, but it would be a different wavelength. So if my wavelength initially was, if I used the whole string, the wavelength might be around 1 meter, okay? But then if I pinched it halfway down, I've just decreased the wavelength. That's going to increase the frequency of the sounds, and it would be the next, like if I played C and then I pinched further down, I could make the next C in line, okay? I think that's how that works. I'm not very musical, but it's something like that, okay? Yeah, so that's what we're looking at there. Okay, so standing wave patterns arise because identical waves travel on a string in opposite directions. They combine according to the principle of linear superposition that we talked about, okay? And that makes those different patterns of interference, okay? The antinodes and the nodes. All right, we already watched those De Cominero's ones, so we're gonna go past that. All right, when we have a wave that approaches a fixed end, okay, Tyler was the fixed end this morning, right? When that wave approaches that fixed end, that is an infinitely dense boundary. Okay, the wave cannot get into that new medium, so it reflects off of that point, inverted, and comes back. Okay, so it reflects off that, inverted, and comes back the other way. That's why there's always an antinode at the end, because the wave is always creating its exact opposite at that point. All right, so there's always going to be an antinode at each end because of that. Right, those reflected waves keep coming back, and you keep getting waves that are, again, the same frequency, same wavelength, so they always interfere at the same places. All right, so here's what I was talking about with a guitar. Okay, if I use the entire length of the guitar string, okay, when I pluck it, it's going to oscillate with a frequency of 165 hertz, and the wavelength of the sound will be what? A 120 centimeters or 1.2 meters. Remember, this is only half of a wavelength here. Okay, there would have to be another part of it over here. So the wavelength of this sound would be 1.2 meters, and the frequency would be 165 hertz. Okay, if I use half of the string, okay, then my wavelength decreases to 0.6 meters, and I get a frequency that's twice what the first one was. Okay, I half the wavelength, so I get a frequency that's twice as high. So this would create a higher pitched sound than when I use the whole string. All right, everybody okay with that? Now, this is an electric guitar. Okay, so the sound created by the string is picked up by essentially a microphone, a pickup. Okay, and then it's amplified electronically. If you're playing an acoustic guitar, then the string vibrates over the hole. Okay. The vibrations of the string go into the resonance cavity. That's the body of the guitar. Okay, because of the shape of the guitar, okay, those waves bounce around inside, off the inside parts of the resonance cavity, and they resonate. That is, they interfere constructively with each other, and they form a standing wave pattern in the air. Okay, so it's a standing wave pattern made of sound waves rather than made of waves on a string. All right, so because the string is vibrating, the air also vibrates at a resonant frequency. That goes into the resonance cavity and is naturally, without any energy, amplified through constructive interference. Okay, then it re-exits and we hear that sound. Right, if you cover up the hole and pluck the string, basically nothing happens. You hear just the string. It's not very loud, okay, because none of those vibrations were allowed to resonate within the cavity. All right. Okay, so in wind instruments, the vibrations are produced differently. In a string instrument, you pluck the string, it's obvious. Okay, but in a wind instrument, you might produce the vibrations with your lips. Okay, so if you play like the trumpet, okay, or any of like the brass, okay, then you have to purse your lips and kind of like that. I don't know how that exactly works, but that's what you do. That's why there's a spit valve in those. I discovered that there's a spit valve in brass instruments, which is like really gross. But anyway, okay, yeah, so the vibration of your lips is amplified by the shape of the horn. Okay, the shape of the horn allows the standing wave patterns to be set up essentially within the body of the horn. Okay, and then of course it exits out through the, I don't know what the end of the horn is called, the end of the horn, whatever that is. Okay, so we get air columns, okay, to resonate to make those sounds. Okay, if you play something like the saxophone, then there's a reed. Okay, you blow across this into the mouthpiece, and there's a reed that vibrates up and down. Okay, and those vibrations cause the air around them to vibrate, and it's channeled and focused through the shape of the saxophone. Now, if you want to create different sounds in a wind instrument, you need to change the length of the column of air. Okay, you don't change what's going on with your lips or the reed. You change the length of the column of air, which is why brass instruments have keys. Okay, so you press on these keys and it opens up different holes for the air to escape. Okay, when you allow the air to escape out of a different hole, you shorten or lengthen the column of air that's vibrating. And by shortening or lengthening that, you change the wavelength, and that will change the frequency that's produced, because now you're altering the conditions. You're not changing the frequency of waves you already made, you're making waves with a new frequency by changing some of the other givens. All right, everybody okay with that idea? Okay. All right, so there's two kinds of air columns. There's open air columns and closed air columns. Most musical instruments, like wind instruments anyway, are open air columns. That means they're open at both ends. Okay, all of the reflections occur along the length of the tube. Okay? If we're talking about closed air columns don't have as wide a range of frequencies that can be produced because they're simpler. Okay, so a very simple closed air column instrument would be like if you had a water bottle and you blew across the top of it. Okay, you know how you can get it to hum. Okay, you blow across the top. That's a closed air column. It's only open at one end. It's closed at the bottom. Okay, whereas if you're playing the flute, you blow across the top of it and it's open. Okay, the top is open, the other end is open. Okay, and so there's a greater range of frequencies that can be produced because of that. Okay, all right. I'm going to give you guys a short break here while I get this next demo set up. Okay. All right. So I'm going to show you here what happens with a closed air column. Okay. So what I have here is just it's an air column, but it's a closed air column because of this. Okay. I'm going to hold this tuning fork while it's vibrating over the end of the white tube. Okay, now the white tube is a closed air column because it's only open at the top. There's water down here that the sound waves will reflect off of. So the sound waves will go into the white tube, they'll travel down it, and they'll reflect off the bottom. They'll also reflect off the inside of the tube, but they'll reflect off the bottom, and they'll create, at some places, a standing wave pattern. At other places, they'll create no wave pattern at all. Okay, so what am I going to hear if I'm holding this tuning fork over the end of the tube and then changing the length of the air column? Okay, difference at how is it going to be different? Is it going to be different in volume or different in pitch? This can only produce one frequency of sound. Okay, this tuning fork can only produce 293.7 hertz. Okay, band people, what note is that? 293.7. I know you don't. I just give you a hard time. It's D, by the way. No. So this can only produce one frequency of sound. So what we're going to hear as I change the length of the column is we're going to hear the sound get louder, quieter, as we pass points where there's an antinode and a node. Okay, so at an antinode, the sound will be very loud, and at a node, it'll be very quiet, or there'll be no sound at all. All right, so you have to listen closely, okay, but we'll be able to hear that at different lengths. All right, now, we're also going to use this to figure out what the speed of sound in this room is, because we're going to be able to measure the wavelength of the sound, and we know what the frequency of the sound is from the tuning fork. All right, so here's what we're going to do. We're going to say that the frequency we're using is 293.7 hertz. All right, so Mason, you're going to have to tell me what the measurements are. Okay, so just wherever the water is on the ruler, just tell me where it is when it gets loud. Okay. Here, get louder. What's the number on that one? 29. Okay, so our first antinode happened at 0.29 meters. All right, so that's where our first one was. That was 0.29 there, right? That's the same spot? Okay. I'm not hearing it. Oh, because I'm nowhere near where it should be. That's why. There it is. 88. Yeah, that's about right. Okay. So the next one we hear is at 88 centimeters. So that's at 0.88. I don't think I'll get another one out of this length of tube. No, I won't. Okay, so those are the two resonant points. Could you hear, like, as I'll do this again, but I'm just going to slowly raise it. Just listen to the changes in the volume of sound. You'll be able to pinpoint where the nodes are at and where the antinodes are at, okay, just by listening closely. Like, there's a node right there. Like, there's absolutely nothing coming out of there now. there's another antinode. Yeah? Still at 88, around there. No, was it 80? Okay, no, we're good. We're good. I was just a little worried there. All right, you guys hear the changes? All right, so here's what we're going to do. We're going to look at what that looks like diagrammatically. We used to do this as a lab, but it just takes too much time and we're too close to the end. I don't want you to have another lab report, but we sometimes will do this. The problem that people have with this lab is that they don't like having to like bend down to look at the numbers. So I'm going to be smarter than most people. So they put it up on their desk like this, and then they've got somebody like doing this, and but someone's always standing right here looking at the water level, and then when they're done, they pick it up. What happens to the rubber stopper at the bottom? You don't know how many times it's looked like someone has wet themselves when we do this lab because they're standing right here and they lift this thing up without holding the bottom, and yeah, then the rubber stopper comes out and splashes all over. It's pretty funny though. Okay, I'm not going to do that. Okay, so here's what happened within the column of air at these 2 points. Okay, we know that in order to get a loud sound at 0.29 meters, we had to have an antinode at the opening of the tube. Okay, so what we had was the water was like, let's say about here. Okay, and so what we had was a wave pattern that looked like that. There was a node here where the water level was, and there was an antinode here at the opening of the tube, right? How many wavelengths were in that tube? Actually, it's less than half. So if we draw like what a full wavelength would look like, it would look like this, right? I've only got that much in that tube. Everybody with me there? Okay, so that's how much of a wavelength? 1/4. All right, so 0.29 meters equals 1/4 times lambda. Everybody okay with that? Okay, so effectively that means that for this situation, lambda is 1.16 meters. Right? When we got this 0.88 meters, okay, we had a different waveform in the tube. Okay, obviously the tube was longer, okay, so the water level was like here, right? But we got an antinode at the end again. So what we had in the tube this time was this. It's the next point where an antinode would be at the opening. Okay, everyone follow me there? Okay, so it's the next point where there'd be an antinode at the opening. So how many wavelengths are in the tube now? 3/4 of a wavelength. So this equals 3/4 times lambda. All right, so that means that lambda is one. Look at that. Is that pretty close? It should be pretty close. I used the same tuning fork in both situations, right? Okay, it should have the same wavelength if it's the same tuning fork. Right, so we got 1.17 for that one. That's not too bad. Okay, meters. Okay, so if I know the frequency and I know the wavelength is, let's say we'll just average it, so we'll say 1.165 meters. Can I calculate what the speed of sound is in this room? What formula will I use? What has speed, wavelength, and frequency in it? Oh, we don't remember this one. I told you this is the most important formula in the whole unit. Oh yeah, right. The universal wave equation, that one. Yeah. Okay, kind of important. So I want to calculate the speed. I know the frequency, I know the wavelength. So I'm going to take that frequency, 293.7, and I'm going to multiply it by 1.165 meters. Well, let's see, the speed of sound in here is exactly what it should be. 342 meters per second. Okay, because we know that at 20 degrees Celsius, the speed of sound in air is 340 meters per second. So we're pretty much right on, okay, in terms of our calculations. That's what we would have you do in the lab. We'd have you measure those points, calculate the wavelength, and then use it to calculate the speed of sound in the room. Okay. Nothing earth-shattering, but okay, it's worth seeing at least. Okay, so with closed air columns, here's the thing, guys. I get a sound here at F1. And I get a sound here, again, at F3. But I don't get a sound at F2. Because what's at the top of the tube at F2? A node, right? We didn't bother drawing it because it was hard to measure, okay? But what was happening was they're around like 60 centimeters or so, okay? There was no sound at all because the standing wave pattern in the tube at that point had a node at the top. So there was no oscillation and no resonance. There was destructive interference at the top of the tube, right? So it's important to know that closed air columns will only resonate at odd numbered frequencies. That's why we don't use them as much as musical instruments. They don't have the same range. Okay? Other instruments can resonate at all frequencies, F1, F2, F3, okay, all of them, and thus have a much greater range of sounds that they can produce. Okay? This is basically like, moonshiners sitting around, drinking their moonshine and blowing across the top of the moonshine jugs and having a hoedown, okay? Which gets crazier and crazier the lower the level of the moonshine in the jug, okay? Now, as the level of moonshine in the jug decreases, people are drunker, obviously, okay? But what else changes? The sound, okay? If I'm right at the top of the jug, I have a very short column of air. So I'm going to produce a short wavelength and a high frequency. As I get down towards the bottom of the jug, then I'm going to have a longer wave and a lower frequency. Okay. All right, so with closed air columns, this is what we just saw. Okay, I drew it, but this is a better diagram than I drew. Okay, so in a closed air column, standing wave patterns are formed that always have a node at one end, so the bottom. Okay, and then when they make sound, they have an antinode at the other. So an example of a closed air column would be blowing over the top of a pop bottle. Okay, because closed air columns must have a node at one end, they are only able to resonate at odd numbered frequencies. So closed air columns, okay, are only able to resonate at odd numbered harmonic frequencies. Okay, so we do have a formula that deals with closed air columns, okay, and that is that lambda equals 4 times L. We essentially derived the same thing over here when we discovered that the first resonant point had 1/4 of a wavelength in the tube. That's where that formula comes from. Okay? So for its fundamental frequency, a closed air column will have 1/4 of a wavelength in the tube. That is, the length of the air column is 1/4 of the wavelength. Okay? Or you multiply the length of the column by 4 and you will have the wavelength of the tube. So for closed air columns, okay, at F1, this is the formula we can use. So a question, if you got a problem to do with this stuff, it would tell you the fundamental frequency is this, okay, or calculate the fundamental frequency so that you would know I can use this formula, okay? If it's talking about another point like what we did here, okay, we would have to know that when we got this point, there were 3/4 of a wavelength in the tube and calculate from there, okay? So most of the time, we're going to be dealing with the fundamental frequency. Okay, so like we said, the first one, 1/4 of a wavelength. The second resonant point, 3/4 of a wavelength. This is F1, this is F3, okay, F5, and so on. So it's the number of quarters basically. Okay, F7 is 7/4, F5 is 5/4, F3 is 3/4, okay, F1 is 1/4. Right? Always going to work that way. Everybody good with that? Okay, so in open air columns, both ends of the tube are open. All right, so the reflections that occur actually are occurring off the inside of the tube, the edges of the tube. Okay, so there's reflections that are going on there, okay, and they channel around and they form standing wave patterns. But you can see here, okay, that there's a standing wave pattern not every half a wavelength, but there is one every half a wavelength, whereas in the other one, there wasn't one. Okay, there was a gap, and then another one, and then a gap, and then another one. This one resonates at all frequencies. Okay, so we get a much wider range of sounds. The difference is, though, that in an open air column, the first standing wave pattern has how much of a wave in it? Nope, half. Yeah, this is half a wavelength, right? Because this is a quarter, right? There's only half a wavelength in the tube right now, right? That's why it says lambda over a half. I was setting you up there. Okay, this one has a full wavelength. Here's a half a wavelength plus 1/4 plus 1/4. Okay, that's F2. So this would be F1, this would be F2, this would be F3, and this would be F4. Notice there's antinodes at all of them. Instead of, with the closed air column, there was an antinode, then there was a node, then there was an antinode, then there was a node. It only resonated at odd numbers. These will resonate at all. So that means that the formula for calculating wavelength for an open air column is different. The first time we hear a sound in an open air column, there's half a wavelength in the tube, not a quarter, right? So we don't say it's lambda equals 4L. Now we say it's lambda equals 2 times the length of the tube, because the tube has half a wavelength in it. Okay, questions there? All right. All right, so we're going to go over a couple of example problems to do with standing waves and air columns, and then I'll have you guys try a few on your own here. All right, so in this question here, I've got a tuning fork. Okay, it has a frequency of 384 hertz. So they told me F. Okay, 384 hertz. It's held above an air column. As the column is lengthened, so exactly what I did, okay, a closed pipe resonant point is found. When it's found, the length of the air column is 67.5 centimeters. We'll just turn that to meters right off. Okay, so 0.675 meters. All right, what are the possible wavelengths for this data? All right, so basically they're saying this may or may not be the first resonant point that was heard. Okay, that's what they're saying here. This is where a resonant point was found, but they're not telling us which resonant point it was. All right, so if it was the first resonant point, what would the wavelength be? No, it'll be longer than this. Remember, for a closed air column, lambda equals 4 times L. Okay, so if this was the first one we heard, we would be looking at this situation here, where there's 1/4 of a wavelength in the tube. Okay, so if it is F1, okay, then lambda would equal 4 times that number. Okay, so 2.7 meters would be our wavelength. Okay, if it wasn't the first one, then it could have been the second resonant point. And at the second resonant point, okay, so this was 1/4. This is how many? How many wavelengths are here? 3/4. Okay, so if it was the second resonant point, then the 0.675 is equal to 3/4 of a wavelength. All right, so I take this 0.675 and I divide by 3/4. Okay, so if it was the second one, that means the wavelength of the sound is 0.9 meters. All right, so they're saying here now that if the speed of sound is known to be slightly greater than 300 meters per second, okay, what is the actual wavelength of the sound? So all we have to do here basically is confirm, is it this one, or is it maybe another one after that that we haven't calculated yet? So if I take 2.7 meters to be the wavelength, and I know the frequency is 384 hertz, okay, V equals F times lambda. If I multiply this number and this number together, am I getting anything anywhere near 300 meters per second? No, I'm getting like 900. Okay, so that resonant point that we measured at this distance is definitely not this one. Could it be the second one? If I go 384 times 0.9, does that get me a little closer to 300? It does. Okay, it's like 330 or something like that, right? 345. That's pretty reasonable for a speed of sound. So I would say that that resonant point was probably the second one. Okay, in that case, I've never asked a question that was convoluted like that one. Okay, most of the time mine are pretty straightforward, right? But that just shows you, okay, what we have to do with the diagrams. We're going to skip those. Okay. Okay, let's look at number 3 here. So I have a standing wave that is generated in a string that is 6 meters long. All right, so I know the length of the string is 6 meters. The standing wave pattern consists of 3 antinodes. All right, so that means it looks like this. All right, and I know that this distance here is 6 meters. Okay, if the frequency used to generate this wave is 2.5 hertz, what is the speed of the waves on the spring? Okay, so if I want to calculate speed of waves, I'm probably going to be using this formula, I would think, right? V equals F times lambda. I have F, it's 2.5. How do I get lambda? Okay, I know that this pattern here is 6 meters long. How many wavelengths are there? 1.5. Okay, so can I figure out how long one wavelength is? I'm going to go 6 and I'm going to divide it by 1.5. Okay, there's 1.5 wavelengths in 6 meters. So if I divide 6 by 1.5, I'll know what one wavelength is. Okay, so I go 6 divided by 1.5, right? And the wavelength of these waves is 4 meters. Okay, now I can calculate the speed of the waves. 4 times 2.5 is 10 meters per second. All right, so is it important to be able to look at a wave pattern and identify how many wavelengths there are? Yes, okay, that's a skill you're going to have. Okay, I want you guys to try number 4. Okay, similar to what we just did, but slightly different. Okay, so it's telling us here that a spring is stretched to a length of 8 meters. So we know the length of the spring. Okay, and we know the speed of the waves on that spring is 5.0 meters per second. Okay. The simplest standing wave pattern for this spring is that of a single antinode between 2 nodes at the opposite ends of the spring. So basically they're saying, here's what you're looking at. That's the wave pattern that's on the spring. Okay. That length is 8 meters. So how long is the wave? 16 meters, okay? Because this is only half a wavelength, okay? So we can go from there that wavelength is 16 meters, right? So what's the frequency that produces this standing wave? Well, I can use the universal wave equation now to get that because I was able to use a diagram of the wave to get its wavelength, right? So frequency will be V over lambda, so that'll be our 5 over 16, okay, and that'll tell us that the frequency there is 0.313 hertz, okay, so less than 1 hertz, okay, 0.313 hertz would create that standing wave. Now, what's the next highest frequency that would produce a standing wave? All right, so that's how fast I have to shake it to get one antinode. But if I want the next standing wave, I have to shake it twice as fast. So I just take that number and I multiply by 2, 0.625 hertz. All right, so you don't have to draw the whole thing and do all the calculations again if you understand that harmonic frequencies are always multiples of each other. Okay, the second one is twice the first, the third one is 3 times the first, and so on. Okay. All right, questions on number 4? All right, so for this one here, we've got a closed air column and its fundamental frequency, so F1, okay, is 256 hertz. Okay, we know that for closed air columns, because we just learned this, that lambda equals 4 times the length of the tube for their fundamental frequency. Right, that's one of the formulas that we just went over. Okay, the speed of sound in here, or in this room where this is happening, is 343 meters per second. All right, what is the length of this air column if the speed of sound is that? So can I calculate the wavelength right now with the information I have? How's that going to help me get the length of the tube? Yeah, I'll divide it by 4, right? I know that what we're looking at here is a closed air column at its fundamental frequency. That means that I only have 1/4 of a wavelength in the tube. Okay? If I can find out what the wavelength is, which I can, then I can calculate what the length of the tube is by dividing that by 4. Okay, so I'll take my V over F, so that'll be 256 divided by 343. Okay. Sorry, other way around. I did that backwards. 343 over 256. Okay, so 1.34 meters. Okay, now that I know that, I can divide that by 4, right? Because if I manipulate this for L, it means divide both sides by 4. So the length of that tube is 0.335 meters. Okay, everybody with me? That's exactly how air column questions are going to work. Okay, you're going to almost always be dealing with the fundamental frequency or be asked to calculate the fundamental frequency, and then the question might have as a part B, what would be the third sound you would hear? Okay, or something like that. Okay. All right. I'm going to put the standing wave worksheet up on the board here, and I want you guys working on that here for the next little while. Okay, the standing waves questions start at the bottom of page 5 and go on to page 6. Okay, so we already did number 1, right? So you guys can start on number 2. Make sure you're paying close attention to what kind of air column it is. Closed air columns, remember it's lambda equals 4L, but if it's an open air column, lambda equals 2L. Okay, so you just got to make sure you're looking at what type of air column it is. You're going to run into a couple of questions on this sheet where you have to use this formula. Calculating the speed of sound in air at various temperatures. We talked about this before Christmas. Okay, 332 meters per second is the speed of sound in air at 0 degrees Celsius. Okay, for every degree Celsius change, there's a 0.6 meter per second change in speed. So you take 332 and you add it to whatever 0.6 times the temperature in degrees Celsius is. All right, if that's below 0, then it'll be like subtracting, but okay, that's the formula that will calculate you the speed of sound in air of different temperatures. So if a question gives you a temperature, it means for you to use this formula to get the speed of sound.